SwayamPrabha. Digital India. Educated India.
Welcome to the NPTEL online certification course on structural systems in architecture. This is module number 3. We are going through the module number 3, the structural mechanics, and today is the last part of the bending stress on beam. So, this is the part 3 and this is the in serial the lecture 13. So, this lecture we will go through this concept of the advantage of the flange beam, that is one of the initial concept that will be covered in this particular lecture. We will see the built up beams, the sectional modulus of the asymmetric kind of a cases. Last lecture we have seen the sectional modulus for the symmetrical sections, where the y max and the top and bottom is equal, and section beam the beam sections with the composite material also. So, the learning objectives of this particular the lecture will be we will apply the bending equation for the various sections, and we have to justify and the advantage for the flange sections to chosen for more case more general cases of the other type of sections, why we choose. We will also outline the theory of bending conceptually in beams and the composite material, what composite material beam cases, how this theory of bending is applicable, which sometimes important because we sometimes use some of the composite material as our structural members, like the concrete. RCC is one of the material which is a composite material. Now, let us first discuss what is the advantage of the flange sections. So, before going to the flange section, let us very curiously see this particular stress diagram, stress distribution diagram over the section of a beam because of bending. So, the two top and bottom part, the topmost and the bottommost part, you see the bending stress is more. That means you require more material over there to resist the bending stress, or to pull down the stress in the permissible limit. But you see, if you see the central portions near to the neutral axis, near to your CG axis of the beam, in the very central portion of the beam, you see the bending stress is less, it is very less amount of bending stress. So, with compared to the top two portions, it is required less amount of material, it does not require that much amount of material, right. So, the material distribution also should follow the stress distribution from top to bottom, such a way that I can eventually use the material very the effective way, and we can produce the economical kind of a beam sections. Okay. So, here if I go through a beam which is a rectangular kind of a beam, I am actually feel very bad, because these two portions which is near to the near to the neutral axis or near the center, I do not require this portion anymore, any material anymore, because I know that this particular portions is having less amount of stress. You see, this amount of portions is under the very less amount of stress. So, why all through the same amount of material should I give for rectangular sections? Yes, some of the beam we cannot help, you cannot actually cast this kind of concrete beam, but some other material we can think of something like this kind of beam. Okay. So, to reduce the amount of material, to economize the total the cost of the structure. Eventually, we have some kind of a beam, we have some kind of a steel gives us some kind of solution. So, steel we can have some kind of a I beam, it is called the joist. This is also called the rolled beam. this is also called the I section, very popularly called as the I section. It looks like a English letter I, and in this there are two flanges, top and bottom. They called as a flange, and the central portion is the connecting portion of the flanges is called the web. Now, you see, as we have discussed in the earlier cases, that this distribution and the material concentration point of view, see this flanges, both the flanges are, you see, it is thin, but it is wide. So, it is having more material concentrated in the top and bottom, which required in the high stress zone, whereas the waves are deep, long, thin, deep, but the concentration of the material, if you take per depth, is not that much, So, this depth is thin and high because it is going to be increase your if it is deep, so it is increase your Ixx and the Zxx value, right. So, this kind of a section, if I say it is I sections, and I can have a series of I sections which does not change its depth remains same, but its the flanges increases, right. The flanges is increases. Suppose this is your 100, so this is maybe 125, this is maybe 150, something like that, this is increased. So, the depth remains same, the flange width of the flange is increased. This is called the wide flange sections. So, we require this kind of section sometimes to take care of the heavy amount of bending moments also. There are other type of sections also, where the same we will not going to change any the width of the flange remains same, but the depth of the section increases, the wave depth is increases. Suppose this is the depth is 100, so this may be 125, this may be 150, something like that, we can increase the depth. So, this is also good. So, this is also good, and this kind of the sections are also sometimes required to take care of the bending moment, because with increment of the depth of the sections, you can increase your the I value, Ixx value, and eventually you can increase your Z value. So, I have calculated some of the flange, wide flange sections. See, this in this case, the bottom 100 is the web. So, if I just draw over here, so if this is the I section, the center one, this 100 is, that means this is your 100, this is your 100, and this is 50, 50 means this is the width is 50, this is 50, and this are the 50. Okay. So, and this is the width 50, I have already written over there, and so and all thickness are kept as 10. This is also 10, this is also 10, this is also 10. So, based on that, I have calculated the area. So, as I increase the width of the flange, the area is increasing, moment of inertia is also increasing, and moment of resistance is also increasing. I have kept some value of 250 as the sigma permissible. So, I have also found out the MR by area, the moment of resistance by area. This figure is very important figure, or very interesting figure to watch out, because I have actually has to pay for my structural systems, or because of its weight. So, its cross section area and the length, total volume of the thing, okay, that gives you the weight. So, the area of a sections is very important for me for the cost point of view, and MR is the moment of resistance is very important for me for the strength point of view. So, as this particular area is smaller, I am very happy, because I have to pay less, right, the cost will be less, and MR has to be increased, so that my beam is much more strong. So, thus MR by area, this ratio, if it is higher, I will be very happy, because the less area, high amount of the MR. So, see, it gives you considerably increasing the value of the MR, sorry, the MR versus area. So, I can go for the wide flange sections, that is why it is beneficial for me. So, I can actually see if there are very close, but eventually this is very beneficial for me. So, I can actually think something like that. So, this blue lines are wide flange sections. something like that. But if you increase the depth, if you increase the depth, now see here I have increased the depth from 50, because this the depth is this is started from 70 and then it is going to 95, 120, 145 and 170 like that, and the flanges remain 100 always same. Now there is no change in the width of the flange. Area I have calculated, which is increasing. Mi, the moment of inertia, increasing. Mr is also increasing. Mr by area is also increasing like that, but considerably high amount way. It is, the jump is very high. This jump is very high with compared to the jump for that, right. So because of the height increasing, this jump is much more, and at some point it's overshoot the wide flange sections. So this particular, for this to calculate this particular the I sections, this thing I have a small sheet on the Excel sheet where you can put your values and you can find out lot of things. Suppose if I put the bottom flange of, suppose it is if I say this is the bottom flange is 200 and 200 and this is your suppose 25, top flange is also suppose 200 and this is your 25 and this is 500 by 10 suppose, then you will see your what is your the CG of the section, that is 275 from the bottom, the moment of inertia, the total depth is 550 and the y top, y bottom and everything is there. So, the z bottom, z top, and this is the MR, the moment of resistance of the sections, and those are the stress in the top and bottommost. So, the stress of the top and bottommost sections is like this. So, suppose if I put something higher value, than 721, suppose if I put 800, then you will see that those stresses will be fail. This will directly changes to the fail, because the stress is much more, 277, which is much higher than the 250 compression and tension. So, that way you can actually see the all the things are can calculate by virtue of this Excel sheet. So, let us go again. So, in the next we can go think of some kind of a built up section. Sometimes you need more amount of moment to be controlled or moment to be actually support. So, we can with the I sections we can go with lot of variety. We can go with we can go with some kind of plate, introducing some kind of a top and bottom plate. We can use some kind of a channel section. We can actually go with some kind of a angle sections and the plate. This is the plates, these are the plates, or some two channels can be put together and make a box sections kind of a thing. Okay. So, like that there are ample way to go for a geometrical construction of those different sections and different kind of the built up beams. Okay. Now, let us go to another kind of a criteria where we can see there are the sectional modulus, and also for this particular built up beam also let me again go back to the another Excel sheet where I have introduced this top plate and a bottom plate along with the top flange wave and the bottom flange, right. And now, if you just do not put any top plate and the bottom plate, it is only because of these three values, then it is a I section, it is a typical I section. If you just put some top plate, suppose if I put 120 by 15 mm top plate, you see that things will be going to change. Okay, the MR is now 267. If I do not have initially what was there, if I do not have, it was 225. Please remember, it was 200. Suppose 225 was there. Now, if I put that value as 120 and 15 definitely it is increasing to 267. 267 it is increasing, see. And then if I again, now there is no bottom plate. Now, if I see again give a same bottom plate 250 by 15, suppose same there bottom plate, it again increased to too much. It is now increasing to almost about 400 and something, 450 47 or something like that. So, it is increasing by. So, if you put the bottom plates, if you put the top plate, then the automatically the beam, the moment of resistance of the beam is going to increase. So, let us go to the back to the PPT again, and that is why we put the different type of the make the sections deeper and heavier and all those, and sometimes go for those kind of some industrial structures, railway stations, and maybe stadiums and all, we can go with this kind of a heavy sections also. Heavy sections are also used for the high rise buildings also. So, the sectional modulus of the asymmetric kind of section. So, initially in the lecture number 2 in this particular week, we have seen the sectional modulus for the symmetrical sections, where this Z top and the Z bottom we calculated based on the Y top and the Y bottom. Y is the fiber distance from the neutral axis to the top and bottom, and for the symmetrical section it was equally apart from the top to bottom, but sometimes it is not so. We can have asymmetrical sections. So, we have the different values of the Y top and the Y bottom. So, if there are different values, so but in the neutral axis your pivoting case will be there in the neutral axis. So, the neutral axis will be the stress is equal to 0, and this is a straight line. Okay. So, as the Y top is higher than the Y bottom, then the Y sigma top will be higher than the. So, this will be the bottom. Lot of mistake I have made in my PPT today. So, this will be bottom. So, that will be the higher, this will be definitely higher, and this will be smaller. And the asymmetrical beams, beam sections will have two sections modulus. So, it will have a Z top and the Z bottom, because as you know the Z is nothing but the Y max, Ixx by Y max. Here I cannot have a single Y max, right. I have a bottom Y max from the neutral axis to that will give me the tensile stress, and I have a top Y max which will give me the compressive stress. So, I have two such Z bottom and the Z top has to be calculated from there. Okay. So, in the Excel sheet I will send this Excel sheet to the forum, or maybe I have uploaded these things in our web. So, such a way you can use that, and you can go to some kind of a different values of, you can give some different values of the flanges, top flange and the this bottom flange, that gives you the different types of Z, so different values of the Y top and the Y bottom, and that will you can see the Y top and the Z top and the Z bottom also will going to vary. Now, there are some of the asymmetrical sections examples. As you see, it won't give you the CG exactly at the central depth. So, the Y top and the Y bottom will going to change. Here it will be something like that, here it will be something like this, this is the U will be something like that. So, like that it will be here. So, now let us go for a small problem solving. So, this is the bending moment. This particular T sections has to encounter a bending moment of 20 Newton per meter. So, you have to find out what are the bending stresses at the top and bottom. So, I first find out that the CG will be at 107 from the bottom. So, as it is 107 from the bottom, the top fiber is 53 from the neutral axis. So, these two are not equal, okay, it won't be, and the distribution, stress distribution diagram will be like that, and the sigma C will be smaller here and the sigma T will be higher here, because the neutral axis is above, I mean closer to the top. So, the stress will be closer or smaller and the top, and the funnel effect, due to the funnel effect it will be higher in the bottom. So, the top and bottom we can calculate like this with this formula what we have seen. Let us go to the next, and I have found out the I value also, the moment of inertia value also over here, and then the same values of the sectional the neutral axis I have kept, and now what I did is that I can find out the Z top and the Z bottom by virtue of this. this is, see, the I will be remain same in both the cases. In case of a top, I have to put the y top, which is 53, right, this is 53, and the z bottom, suppose if I take as some different color, z bottom is this, which is 107, which is z bottom, okay, the sectional modulus bottom. So, we have got two such values, right, and the stress, if the moment is 20 Newton per mm square, the stress at the top will be your m by z top, that is 159.15, and the sigma and the bottom will be the m by z bottom, that is 62. So, it is 312, 321. So, definitely this is very high with compared to this. Okay. So, next we will see another problem that this particular I section is asymmetrical, because this is 120 by 20 and that the top one is 60 by 10, and in the compression and the tension, the permissible bending stress in the compression and tension is not equal. Compression it is 250 and the tension it is 150, it is little less. Now, how much bending moment of resistance of this I section, how much bending moment I can actually give load on this particular beam. So, I found out the CG and all. So, CG and all I have found out, and then the moment of inertia is also found. You can also do this same calculation by virtue of that Excel sheet. So, I know the bottom will be in tension, it is a case of a sagging, and compression will be in the top. Now, I found out the top z top and the z bottom. I know this is the I. So, I know this is the top y top. So, I can found out the z top. Similarly, the Ixx, this is Ixx, and this is your y bottom 42.25. So, those are the x and z bottom and the z top. So, those value you can compute, or you can use the Excel that format to compute these values. Now, let me clear it. Now, see, this is the stress distribution of this particular, the top will be smaller, higher, and the bottom will be. So, it will be pivoted at this particular point, and the neutral axis will be lie over here, and because of that the sigma c, that is the stress in the compression zone, will be higher with compared to the stress in the tension zone, because the neutral axis is near to the bottom, near to the. Remember, in the last the example we have seen that the neutral axis was towards the top, that is why the top fiber stresses are less with compared to the bottom fiber stress. Now, if you remember, we have told that the sigma c permissible, that is the compression permissible, is 250 and the tensile permissible is 150. Now, the sigma c by sigma t, there is a relation. There is a relation governed by this particular, these two are the equal triangle, and I can say that this sigma c by sigma top, this is from the property of the triangle, equal to the sigma t by sigma bottom. So, sigma top and I am sorry, the sigma c and sigma t I have to found out with respect to the y top and the y bottom. So, y top and y bottom value if you give, so you can find out a relation like sigma c is 2.0, almost 2 times of sigma t. That means, whatever may be the value of this, it will be the almost twice of that, and it is higher because it is the neutral axis is lower towards the end or the bottom. Now, let us I first put that the sigma t is 150 Newton per mm. So, why 150? I put the, I know the sigma t can go maximum 150 as a permissible limit. I cannot put it sigma t 151 because it will going to fail. So, if it is 150, then sigma b has to be 312. Why? The relation between sigma c and sigma t is sigma c equal to 2.08 sigma t. So, this gives me So, should I go with this combination? I cannot, because it is in red color, because see, the permissible compression in the material is only 250. So, if I put 150 as sigma T, the sigma C become 312, which is beyond the permissible limit of the compression zone, and this will going to fail. So, I have written over there, it is more than 250 and stress is more than the permissible stress, beam will fail in compression. So, it is unsafe. So, I cannot have this proposition that the bottommost fiber or the bottommost portion will have the limiting case of the tensile stress, and correspondingly the compressive stress will be much higher with its limiting case of 250. So, let us go to the other case around. What is the other case? This is the relation I know, I have again put down the relation, and now I assume that the sigma C, if it is 250, why 250? Because this 250 is this is the compression permissible for the compression zone is 250. So, if it is so, the sigma T will be 250 by 2.08, which is 120 Newton per millimeter square, which is much less than the 150. 150 is the limiting permissible case for the tensile case. So, it is 120 is okay, that is why I have marked it in green color. So, it is less than 150 and stress is less than the permissible, and that is why it is safe. So, the earlier case was not safe. So, in the safe cases is that the topmost portion should catch the compression, which is highest compression or the permissible compression, that is 250 Newton per mm square, and corresponding to that the bottommost part will have 120, and that is safe. And based on that, MR will be Z into sigma. The Z values of the topmost portion is your the calculation is there. This is there, and then we can find out the sigma, the moment of resistance as 29.4 kilonewton per meter. So, this is another problem. So, here I have kept a particular channel sections as this particular the beam, and the T have to find out the values of T such a way that this both compression and the tension achieve simultaneously. So, for that I have to see that I have to achieve this as 200 and achieve this as 100. So, what should be the value of x such a way that I can achieve? So, what should be the neutral axis value such a way that the pivoting point rotates such a way it will actually catch the 150 as 200 and 100. So, for that I know the total depth of the section is 120. So, if it is x, this is 120 minus x. So, 120 by x, so this is the from the similar triangle I can find out. So, I can finally say that x is equal to 40. So, x has to be 40 and the upper portion has to be 80 such a way that this hinge should be such a way that the sigma compression at the top will be 200, and at the same time the sigma tension will be the 100 in the bottom. So, I have then found out the CG of the sections like this, as you know, and equate that to 40 to find out the value of T. So, by calculating I found out the value of T as 16 mm. So, the 16 mm has to be the thickness of those two stands to make it possible that both the compression permissible and the tensile permissible 200 and 100 achieve simultaneously. The last one is the composite material. So, suppose this is a wooden timber beam of 100 by 200, and this is the sigma value of that because of the moment and all those kind of thing. So, 75 is the kilonewton per meter is the moment. So, this is the stress distribution, but if I put the two steel reinforced plate on the top and the bottom, we will have the E values of the steel is 2 into 10 to the 5 and E timber is 1.1 into 10 to the 5, very less. So, what is going to happen is that there will be two compatibility conditions at this point where there is a meet. In this particular point there is a strain compatibility. In the strain compatibility, the strain has to be equal, and from this strain compatibility we may say that the stress in steel must be equal to what is M? M is this. What is this? If you remember, it is modular ratio times sigma t. If you go for the radius of curvature compatibility, because radius of curvature also has to be equal and these two phase or these two interface of the timber and the steel, otherwise one will slip with other. So, in that also we can say that sigma steel, the sigma, that means the stress in steel is equal to modular ratio into the stress in timber. So, in that case what we did, our original section has to be enlarged to equivalent timber sections, where I increase the sections of the steel by multiplying the dimension of 100 by 20, and 20 is nothing but the modular ratio. So, now the timber sections is equivalent timber sections look like this is as it is 300 by 100, but there are two such enlarged portion of 2000 by this is 10, and because of that you can find out the moment of inertia, you can find out the sigma t and sigma t for the stress at the timber junction. So, stress at the timber junction is this. So, the stress in the steel at the junction is m times, so 20 times of this, so almost like 972, and the stress in the topmost portion I have found out, like first I found out the what is the stress in the sigma the timber, and we multiply with the m, that is the value of the modular ratio. So, it is almost like that. So, like that you can find out the stresses for a different portions of a composite sections, which will be important for your RCC design. Of course, that RCC design is not included in our the course. So, I have taken the reference of this following books. The flange beam is effectively used as a beam sections, which is very much important and very much effective, and the composite beam can be used to improve the moment of resistance of the capacity of the beam. So, I have given you 3 homework here. So, first is a composite section kind of a thing, and second one I sections, the flange sections, you have to find out the moment of resistance of the I sections and impose load and all. And the second case, if you use the two plates over that, then what is the change. And here also I have the similar problem I have given you, where with a plate, but it is a single plate at the bottom. So, you have to find out the stress in the wooden beam only and stress in the steel plates, Okay. So, the junctions of the steel plates also. Thank you very much. This is the end of lecture 13.